In this module, we're going to discuss the formation of a solar system and specifically where the planets come from.
When we actually look at the solar system, we see today, this is looking at it now as it is at the moment, the solar system has a few features that are actually directly derived from, as a result of its origin. So one of those things is, if we viewed the solar system from above and looked down upon it, I'll show you a figure in a moment, all of the planets would rotate in the same direction around the Sun. So if you view it from above, they'd all go in the clockwise direction. Now, due to things like the conservation of angular momentum that we've already discussed, this means that the original solar nebula from which our entire solar system formed was rotating in a clockwise direction when viewed from above. So this is the kind of thing we're talking about. Again, notice that all of the terrestrial planets fit down in this tiny circle here. So they are blown up and taken off to the side so you can see them in more detail. But we're talking about organized rotation. If we view the entire system from above, all of the planets are going the same way around the Sun. They're not all necessarily rotating in the same direction in terms of their day, in terms of the Earth rotating this way, as you can see Venus is rotating this way, but they're all going the same way around the Sun. We also have a distribution of planets. Now remember this part when we talk about exoplanets and planets in different solar systems, because they're a little different. But when we look at the distribution of planets, we see that the terrestrial planets, the small rocky planets, things like Mercury, Venus, Earth, and Mars, are all close to the Sun. And the Jovian or gas giant planets, those terms are interchangeable, Jovian meaning Jupiter-like. So the gas giant planets, large gas-rich things, are further from the Sun. And then you get much further from the Sun, you end up with little icy bodies like Pluto. And as I'm talking about this, a probe is getting to Pluto, so we'll know more about that very world very, very soon. And then we have things like Kuiper belts, and the Oort cloud, which are really sort of remnants left over on the edge of the solar system. And that's one of the arguments with Pluto. Is it one of these objects, or is it really a planet? And there's our close-up of the solar system again. Excuse me. So, this is what we're seeing here. Everything rotating around the Sun in the same direction, and here's Pluto doing its strange thing on the edge of the solar system. Gas giants, all arranged here, and all the rocky stuff, including an asteroid belt, very close to the inside. Now, something to note about the asteroid belt, every time it's depicted it looks pretty busy. It isn't like Star Wars where you fly through, like Empire Strikes Back for instance, flying through an asteroid belt and desperately trying to avoid these rocks hurtling at you. It's nothing like that. It's actually kind of difficult to hit an asteroid. You're talking about billions of kilometers between each one, and makes them very, very hard to hit. So you have two families of planets. And as I said, we have terrestrial planets, and we have what are called the Jovian or gas giant. Gas giant is a more regular way of discussing these planets, but I'll use Jovian and gas giant interchangeably. So the terrestrial planets are small in size, relatively low mass. They have high density rock, and they have a lot of metal in them, and they have solid surfaces, and not very many moons. If you actually look at the terrestrial, the rocky planets, the Earth has a good sized moon compared to it, but then we're talking about something that's almost a double planetary system. Mars just has 2 captured asteroids, Venus has no moons, and Mercury has no moons. And of course they're closer to the Sun, which means their surfaces are warmer. Venus being a bit of an exception because of its massively thick atmosphere making it even hotter, but generally they receive more warmth from the Sun than any of the gas giant planets. The Jovian planets, large size, very big diameters, and relatively high masses. They have much lighter materials, far more gases, hydrogen, helium, and lots of ammonia and hydrogen-derived compounds. They have no discernible solid surface. It's possible there's either a solid or a very high-density liquid surface at the core of many of these objects, but as far as something humans could go stand on, no discernible solid surface. And of course, they're further from the Sun, at relatively low temperatures, and their upper atmospheres being very, very cold. In fact, Jupiter is actually putting out more energy and actually radiating more energy into the infrared end of the spectrum than it's actually receiving from the Sun. And then we have a few other things like asteroids and comets. So there's a large amount of asteroids and comets. The icier comets tend to be out beyond the orbit of Neptune and in what we call the Kuiper belt and the Oort cloud, which are clouds or belts of very icy objects formed on the edge of the solar system. And the comets that we see when they come close to the Earth are on very long orbits. They're usually coming out from very far in the solar system, coming in towards the Sun, crossing, say, Earth's orbit, and then going back out into these very long orbits, right out to the edge of the solar system again. And we have a lot of rocky asteroids in very regular repeating orbits between Mars and Jupiter. So here's a couple of pictures. Here's an asteroid. We've actually had a spacecraft land on an asteroid now. We know quite a lot about them. They're usually not circular. They're usually weird, wobbly potato shapes with a few craters and some nodules, and often even peanut shaped, where they have two objects stuck together even. And then you have comets. Comet being down here. I believe this is a picture of Comet Halley when it was going over Australia. Now, comets are icy bodies, and basically they are very, very hard to detect until they get close to the Sun. When they get close to the Sun, they start to eject a lot of gas and a lot of dust, and that's why they look so long and so huge in the sky. Now, comet, the word actually comes from kometas, meaning long hair in Greek, and you're talking about very small bodies, just a few kilometers across on the scale of asteroids, but we're talking astronomical unit length tails on these things. So, we're going further out in the solar system past the gas giants. So just to orient you, here is the orbit of all of our planets. Here's Pluto's orbit. And here's the orbit, here's Pluto's orbit. This is the orbit of a binary object, a double object that was discovered in the Kuiper belt, going around here. As you can see, discovered in 1998. So the Kuiper belt is a relatively flat belt of icy objects in the outer solar system. And one of the arguments that Pluto is not a genuine planet is the fact that it resides quite well inside this belt. So you can see there's a very clear area here on the inner solar system, and then a disk of icy comets and other bodies out here. Now, that's not it. If we go even further out, we can actually see that that disk and our entire solar system fit into this little blue square. So this little blue square blows up to look like this. So the Oort cloud is an enormous, enormous object. And this is a lot of basically dead comets. They don't come close enough to the Sun to actually start emitting any gases. But this is a lot of icy remnants on the very edges of the solar system in a much more spherical distribution than you see in the Kuiper belt. As you can see, there's quite a distribution in a sort of two-dimensional plane here. Now, these things are very difficult to detect. They don't put out a lot of radiation, they don't put out a lot of heat, and they're very far from the Sun. But the Oort cloud has billions of comets in it. And one of the theories about mass extinctions on the Earth is occasionally there could be some star that could come through and disrupt this belt or disrupt the Oort cloud and send a lot of comets flying our way. There was a popular theory a few years ago about this, but we would have probably detected any brown dwarfs that were nearby causing disruptions in the Oort cloud. And remember, the scales that we're talking about here, we're still talking very, very large distances between these clouds. So if you were to navigate a spacecraft out of the solar system, you would be very hard pressed to run into one of these objects. These diagrams can sometimes look a bit misleading in order to show you the distribution. So the take-home message here is that we have a disk of material outside of Pluto's orbit, and then we have an Oort cloud of comets in a spherical distribution outside of that. So a few other things that came with the solar system when we took it out of its box. Uranus is one of the odd parts. And yes, I'm saying Uranus to avoid any giggles from people. Uranus is actually tilted compared to all the other planets. If you look at all the other planets from above, you're looking directly down onto their rotational poles almost, apart from a few degrees difference. Uranus is tilted and is actually spinning at almost 90 degrees to every other object in the solar system. And it's relatively easy to say, okay, it got whacked by a big object and it turned it on its side. But that couldn't have happened, because all of its moons and its debris belts are orbiting absolutely normally. It's just that the whole planet is sitting on its side. The other thing we can look at is that Earth's moon is disproportionately large compared to other planets, making it a bit of an oddity in the solar system. And the third thing that's weird is that Venus rotates the opposite way to all the other planets. So the sun rises in the west and sets in the east. Now you might not think those are that odd, but since everything is going the same way around the sun, you would think that the way that the angular momentum that keeps them spinning was imparted to them would also have them have the same rotation axis. But here's at least two planets with very different rotation axes, one in the wrong direction, well, comparatively wrong direction if we look at popular opinion of rotation direction in the solar system, and one sitting perfectly on its side. So let's take a look at Uranus. So here's the rotation axis of Uranus, pointing this way, and these are its moons, named for Shakespearean characters, Midsummer Night's Dream, and various other Shakespearean plays, and here is its ring system. So as you can imagine, Uranus actually has some quite strange weather on its planet. In terms of the Earth, we have heating at the equator, which then sets up circulation cells that take hot air to the poles where it cools. And then the circulation cells continue to move around, transporting energy. In the case of Uranus, its pole is pointed towards the sun. So its pole is receiving the energy, and this is just rotating round and round this way, which probably gives it some quite odd circulation currents. And that's probably why its atmosphere is, frankly, a relatively boring one, with not much activity. And here are its various Shakespearean moons, Rosalind, Belinda, Puck, Portia, blah blah blah, all rotating at 90 degrees along with the ring. It would be very, very unlikely that another planet came in, hit this planet, turned on its side and then went away, leaving all of its moons undisturbed and rotating in this fashion, along with its undisrupted belts. Rings, I should say. And here's an image taken from a telescope. The University of Arizona credit there. And here's Uranus on its side. Here's its belts. And you can see the dates here. It's flipping through August of 1994. This is a very nice image from a very big telescope. And you can see its various moons rotating around the planet all at 90 degrees. And this is taken at multiple nights. We're now going through August. And there's actually atmospheric features. White, probably ammonia clouds that have formed in its atmosphere, rotating around the planet. And now we're going faster and faster. The effect you're seeing with the rings there is just Uranus rotating relative to us, moving around in its orbit. And as you can see, there are various atmospheric features, thermal atmospheric features, but the planet is happily rotating on its side. There's its pole, and there are its circulation currents, which are, compared to the rest of the solar system, relatively strange. So, possible scientific reasons for the weird rotation of Uranus. Close pass, collision with another large body, something like a planet, something or a moon, maybe even a brown dwarf or something early in the solar system. Problem is, moon system's fine, everything's undamaged, there's no reverberations in any of the orbits. Also, one of its moons, called Triton, actually orbits backwards compared to the rest of them. That's weird. This is actually attributed to what's referred to as an asymmetric distribution of material in the original solar nebula. So as we'll see shortly, when the solar system was forming, it was spinning. It was a spinning gas cloud, and it's thought there was more material in one part of the gas cloud than another. And the way that the angular momentum was distributed, it imparted it to preferentially to part of the disk, and then the vector sum of those angular momenta actually resulted in this particular body spinning on its side. It has been modelled, and it probably is the most likely explanation for why. And trying to figure out why our solar system formed the way it did might help us figure out how solar systems form around other stars and the propensity for life around other stars. So, if you want a good reason, it's probably that different angular momentum was imparted to the outer part of this disk from which the solar system formed. As we mentioned, Earth's moon is relatively big compared to the rest of the terrestrial planets, which have either very small or no moons at all in most cases. The moon was probably created very early on in the Earth's formation, when a large body hit the moon and spun off, taking a big chunk of the Earth with it. So it was probably formed by an impact with a big planetesimal, and that formed our moon. Other large impacts could give you the weird rotations of Venus, and as we said, Uranus possibly, but that theory has fallen out of favour with the discovery of its well-behaved moons. And there's just a pretty picture from the Galileo space probe of Earth and its buddy the Moon, both with the same phase, which should tell you exactly where the spacecraft was in its orbit when it took this particular picture. And here's the kind of thing that probably formed the Moon. Good moon forming event. Here's a primordial Earth very early on in its formation, and then the Moon hits it and spins off and takes a lot of molten Earth with it. The other thing we mentioned was Venus's rotation. Venus has a very slow counterclockwise rotation, and it actually moves 243 Earth days in one Venus day. So it takes Venus one day to spin on it. One Venus day to spin on its axis is 243 Earth days, which weirdly, 1 year on Venus is 225 Earth days. So that's a little strange. Venus's day length is actually longer than its year length. And as we said, it could be a result of collision It could be a result of the way the angular momentum was imparted to this body when the entire solar system formed. It could also be due to a bit of both of these particular situations. A bit of a collision and a bit of lack of angular momentum. So if we were to look at Venus next to the Earth, Earth has its rotational pole here, slightly tilted, and is spinning this way. Venus is spinning this way. And apart from Uranus, every other planet is spinning in agreement with the Earth. So those are the 4 weird features of our solar system that you should keep in mind when you're looking at the solar system. So this is explaining here that large bodies in the solar system are relatively orderly, and these are the 3 particular conditions that we discussed already. So let's talk about the formation of the solar system. So a solar system is basically a star with objects that orbit it, usually planets. Now remember, planets weren't really confirmed by observation until sometime in the late 80s, early 1990s. Before that we had scientific data to suggest they were there, but we didn't really see them as such. So all of these science fiction things that you see where planets are relatively common and people travel around to planets and find them in every solar system they go to, that is actually was at that time complete fiction, but it's something that people came to accept because they'd seen it so much in the media. So it's not long. Hasn't been long since we've been able to confirm that other planets even existed, even though it was probably a reasonable thing to assume. So solar systems are defined as stars with objects orbiting them, usually planets. So material that forms around stars comes from a circumstellar disk. That means a cloud of material collapsed in on itself and formed a star, and the outlying material formed planets, asteroids, and comets. And this is referred to as what is the nebula theory. Remember, a nebula is actually a floating cloud of dust and gas. This is a nebular theory. If you say nebular, it sounds like some kind of bad guy in a comic book, but this tends to get pronounced nebula, very confusing with the word nebula, meaning just a cloud of gas. But the nebular theory states that the solar system formed from this gigantic primordial cloud of interstellar gas. And that cloud, where did that cloud come from, is usually people's next question. That cloud was formed from recycled gas from previous generations of stars in the galaxy. Previous generations of stars in the galaxy exploded in supernovae and put out gas and put out dust, and those constituents were combined into our primordial cloud and then eventually into the planets that we live on. So the original gas in our solar system probably consisted of 98% hydrogen, and helium, and about 2% of other materials. So nearly all hydrogen and helium, and most of that is concentrated in the sun. Now, helium is a very difficult thing to make, so putting it in balloons is actually kind of a ridiculous thing to do. Most of it is encompassed in the sun. So here's sort of typical condensation temperatures and why we end up with a nebula which has the relatively heavy compounds, a few hydrogen compounds like water, methane, ammonia, lots of rock, lots of metals, and not much hydrogen and helium. And the reason being that if you look at these temperatures, about 150 K, this is Kelvin, remember, you end up with the 1.4% of mass of water, methane, and ammonia will actually condense out. Rock needs about 500 to 1300 and 1000 to 1600 to condense out. That means that these things formed outside of the star and condense outside of the star, and the hydrogen and helium, which doesn't condense in a nebula, was taken up into the star itself. So these things went into the sun. These things went into the outer objects. And you can see the majority of the mass, 98% of our mass, is in the sun, if you look at the mass of our solar system. And we don't have many metals at all. So the original solar nebula would have formed in a star formation area, something like the Carina Nebula here, where there's lots of stars being formed in all of these objects. No one has ever actually directly observed a star being formed because they form in very dense gas globules, like this one here. You can't see inside of it, but using infrared astronomy, you can see the heat of this particular object, and you can actually see where these stars are being formed. You can see here these reddish areas. These are stars which are formed inside these clouds and are slowly burning their way out of the cloud. This one's actually got objects throwing material off and producing the sort of weird antennae effect here, and another shock wave doing the same here. So here's kind of what happens, a kind of timeline. A large cloud of gas actually condenses and stars form from those gas clouds. The star starts to generate energy and then blows heavy elements out into space, which get put into the next generation of star formation. So here's a timeline of events. We start off with a very large cloud of gas and probably a little bit of dust, and that cloud starts to contract. So it's a large diffuse gas cloud, and at some point one part of this gas cloud ends up with more mass than another part, and that causes the entire cloud to start to condense. As it condenses down, it'll start to spin. And as we talked about conservation of energy before, as it gets smaller, its gravitational potential energy will be reduced, and that will go in the form of kinetic energy and heat. So using the Kelvin scale, this kinetic energy will go into thermal energy and start to heat up this cloud. That causes the very core, the very center of the cloud, to become very hot, and this is where your star will form. And by conservation of angular momentum, remember the spinning ballerina, as this cloud gets smaller, it will start to spin faster. So the whole system's starting to spin fast and get hotter. So gravity is going to force the cloud to get progressively smaller, keep spinning faster, and the heat at the very center, at the very core, will increase and increase and increase, and it'll reach a point where the heat is so great that fusion can begin. When fusion begins, when you have sufficient mass at the center that you can overcome Coulomb repulsion and force two hydrogen atoms together, we'll discuss this later when we talk about stars, you'll end up with fusion. So massive temperatures and pressures at the core, due to the mass that's there, causes fusion and stops this cloud shrinking. So radiation pours out and the cloud stops shrinking anymore. The next phase, you have collisions between the particles that are in orbit, and they start to form a disk. The collisions force the cloud to flatten out into a disk, and this is the beginning of the disk from which our solar system is going to form. So the material settles into a spinning disk, and that spin prevents the whole thing collapsing in on itself. This COAM here I have here is conservation of angular momentum, and the whole system keeps spinning. And the conservation of angular momentum keeps it spinning. So this is what's happening with the solar nebula. We start out with a large cloud, and it starts to condense and condense and condense, and to spin as it gets smaller. It forms a disk. That disk starts to get smaller and spin around quickly. The collisions make it into a smaller disk, and it flattens out. So if you think about this in terms of the skater, as we were discussing before, the radius of the cloud is shrinking, and we're looking at a conservation of momentum, so L is dependent on mass, radius and velocity. The mass is staying the same, the radius is reducing, so its velocity is going up. So the cloud is essentially pulling its arms in and spinning faster and faster. So a star forms at the center of the system. The disk at this point is usually flattened out and is about 200 astronomical units in diameter. So remember, the radius of the Earth orbit is 1 astronomical unit. So this is huge. So the material that isn't used in the star formation is orbiting the star's disk, and that's what your planets form from. So planet formation and the mechanisms that start planet formation is a subject of ongoing research, and I've actually done research into this and taken observations at very nice observatories, and it actually has a lot to do with how much turbulence there is in the disk, how much material, and a lot of other factors. But if you take observations of a circumstellar disk, you have to really look at the system and block out the central star. Remember, the star is going to be very, very bright, and if you look at the whole system, the star will just mask out any detail in the disk. So this is actually a disk around another star in the universe. We're looking at another star in our galaxy, and this is the disk, and this is about 200 astronomical units here. So very big structures. And here's a close-up image of primordial gas clouds forming in a much bigger gas cloud. And as you can see, this little star here has actually carved a little hole out in this enormous gas cloud. This one's in the process of doing the same, and this star here has its own globule. It's actually a gas cloud that's forming a star as we speak, as is this one. So a spinning disk of gas and dust will remain around your protostar. Protostar meaning a star that's just started fusing hydrogen and making helium. And that dust and gas will form very specific bands, and they'll become what we call stratified. And the dust will settle to the middle of the disk, and the gas will go to the outside of the disk. Think about this as like a sedimentation experiment. If you take sand and pour it in water, the sand will go towards the middle, the water will separate towards the outside. So in this case, the dust goes to the center and the gas goes to the outside. And if the dust density is sufficiently high towards the center, it'll form gravitational instabilities and it'll allow planets to form. That'll give you clumps of material. If the disk doesn't have sufficient density, then your planetesimal formation may be slower. You can also have turbulence in the disk, as I said before, that prevents your clumping. We're not going to worry too much about that. Try to keep this first point in mind, that the gravitational instabilities will form the clumps which form the planets. So the really orderly motions of most of the solar system are a direct result of the birth of the solar system. So the dynamics of spinning flattened clouds, dust and gas, and the orbital parameters of the planets come from the very beginning of the solar system. And our solar system is a really nice two-dimensional flat shape, a bit like a record, apart from a few objects. And this is kind of why. So when I was talking before, I said that collisions occurred between material. Well, as material collides, it tends to form a disk. And just to get the idea across, this is the same simulation we saw previously. At the top, this was the formation of the circumstellar disk. This is the formation of the circumstellar disk from the side. So you can see the cloud getting progressively smaller. This is from the side, and this is turning into a thin disk of material due to collisions and due to condensing down to a smaller object. So here's the actual result of all the various collisions. Looks rather like the depictions of an atom, all these objects colliding until they flatten out into a disk.